6.6, normal as approximation to binomial. We start and we go back and talk about a binomial probability distribution. And if you remember doing a binomial probability distribution, that's the one where we had, like, let's say we had 20 choose 6, and then we multiplied by some probability, and let's say the probability was 0.2, and we're choosing 6 of them. So 6 of them had that probability, and then there would be 14 with the 80% probability. And that was, we used that formula to calculate binomial probability distributions. Sometimes it gets complicated because there's too many numbers and there's just too many to look at. And so what we're going to do is, instead of looking at the binomial distribution, we're going to use a normal distribution to kind of approximate. So one thing that we're going to have to do, we look at this and we have to verify that it will even work. And so when they talk about probabilities P and Q, they're talking about these numbers right here. Probability that it is and probability that it isn't. And then the conditions, we'll come back to this later, but we'll have to look at those numbers right there. N times P is greater than or equal 5. N times Q is greater than or equal 5. So if these two things occur, then we can do what we want to do. We can use this normal to approximate the binomial. Now, if we go back a chapter or so, you might remember these two formulas. These two formulas are going to be important for us to go back and do what we've been doing with the normal. We want the mean and the standard deviation for our normal curve. So we're going to have to calculate it, and we'll use those formulas. I think the weirdest thing about this lesson is this. The binomial probability distribution is discrete, which you may recall means countable. I can count it. But the normal approximation is continuous, which means not countable. And so we have to try to fix the numbers, because we're looking at discrete, we're looking at continuous, we're using a continuous to approximate discrete. So we've got this idea of a continuity correction. And it's kind of a strange idea, but it's easy to implement. We're going to have to look at whatever our x number is minus 0.5 and whatever that x number is plus 0.5. You'll see it more when we get to an example. Brief review of binomial probability distribution. This is stuff we learned before, but we've got a fixed number of trials that are independent, and the trials are either a success or a failure. That's your P and your Q, by the way. And for the trials have the property that the probability of success remains constant. So if it's a 20% chance this time, it's 20% chance next time, next time, next time. So we had these variables in X, P, and Q. We saw in a previous section that the sampling distribution of a sample proportion tends to approximate a normal distribution. So this isn't new. We've used the normal to approximate before. Also, see the following probability histogram for the binomial distribution with n equal 580 and p equal 0.25. In one of Mendel's famous hybridization experiments, he expected 25% of his 580 P's to be yellow, but he got 152, which is a rate of 26.2%. The bell shape of this graph suggests that we can use a normal distribution to approximate the binomial. So what happens is there's just so many different things that can happen, but if you actually calculate all of the things that could happen or whatever with these P plants, you notice a normal curve. And so that's where we're thinking, okay, well, maybe we can use the normal curve to approximate the binomial. In this binomial problem, N is 580, P is 0.25. And so they didn't give you Q, but it's easy enough to figure out Q must be 0.75. Normal distribution as an approximation to the binomial distribution. Here we've got the requirements, and we've already kind of talked about this, but the sample is a simple random sample of size n from a population in which the proportion of successes is p, or the sample is the result of conducting n independent trials of a binomial experiment in which the probability of success is p. So this is just talking about a binomial problem. And then we also have to check that these requirements are met. N times p is greater than or equal 5. N times q is greater than or equal 5. Here we've got the same two formulas here where we find the mean and the standard deviation. So we can draw our normal curve. And again, it tells us about the continuity correction. Remember, we're going from discrete to continuous. So we're going to use this calculation to kind of fudge the numbers a little bit and help us approximate. Procedure. Number 1, check these requirements. Number 2, find your mean and your standard deviation. Number 3, we're going to use that continuity correction. And this is going to change our numbers slightly. When it says identify the discrete whole number x, x is the number that they're looking at, right? They might say we want it to be more than 145 or more than 212 or whatever. So they're going to have to give you this x number, and then we're going to just kind of change the numbers slightly by either adding or subtracting 0.5. 4, we're graphing the normal distribution, so this is going to look exactly like what we've been doing all chapter long. We're going to draw this picture. Here's the mean, here's the standard deviation, and then we're going to look at whatever our x number is, and maybe we shade to the left, or maybe we shade to the right, or whatever we do. We can use our chart, we can use our calculator, use that formula, but we're doing the same thing as what we've done in some of the last several sections. Example 1. In one of Mendel's famous experiments, he expected that among 580 offspring peas, 145 of them, or 25%, would be yellow, but he actually got 152 yellow peas. Assuming that Mendel's rate of 25% is correct, find the probability of getting 152 or more yellow peas by random chance. That is, given n equal 580 and p equal 0.25, find p is greater than or equal 152 yellow peas. Kind of wish it was written like this, but it says the same thing anyway. Then at the end it says, is this number significantly high? So let's look at the steps. Step 1. Go back and look at the steps in your procedure from before. Check the requirements. So in this problem, n is 580, p is 0.25, and so therefore q is 0.75. The requirements say that n p has to be greater than or equal 5. So n is 580 and p is 0.25. If you multiply n times p, you get 145. And sure enough, 145 is greater than or equal to 5. Check. That's one of the requirements. Now check the other requirement, that n times q is greater than or equal to 5. I guess you can put a question mark here because we're asking that question. So again, n is 580. This time q is 0.75. 580 times 0.75 is 435, which of course is greater than or equal to 5. Check. So step 1, check the requirements. Yep, works. We're going to move on to step 2. Step 2. We want to find the mean and the standard deviation. Well, the mean equals n times p, and we just did that a minute ago and got 145. The standard deviation is the square root of n times p times q. N times p times q, that is 580 times 0.25 times 0.75. We've got the square root of 108.25. Or I think that's 7.5. And then when we do that square root, we're getting sigma is approximately 10.4283. So that's step 2. Step 3 is the one about the continuity correction. So in this problem, it says find x. X is just the number that we're looking at, 152. And it's easier than it seems. All we have to do is add or subtract 0.5. The continuity correction says x plus 0.5, x minus 0.5. Basically, we're going to add or subtract 0.5, and we're going to look at 151.5 or 152.5. Add or subtract 0.5. That's it. So we're actually going to use one of those two numbers instead of the 152. All right, and that's what's kind of weird, I think. Step 4 is where we actually do our normal distribution, and we're going to do it in the exact same way as what we've been doing in the past few sections. I think all of you probably need to be drawing this picture more than you actually do, but draw this picture of the normal curve, and we're going to label the mean 145 and the standard deviation sigma equals 10.4283. Now, normally what we were going to do, what we would have done in the last couple of sections, is we would have said that 152 is right here. And since we want greater than or equal 152, we would color in this region right here from 152 to infinity. That's what we're coloring in. Okay. But the problem is we've got to go from the discrete to the continuous, and we have to do that continuity correction. So what we will actually do is we will actually say, well, here's this mark at 151.5, and here's this mark at 152.5. We're actually not using the mark at 152. We're going to use either one or the other of those two, okay? But one of them's right and one of them's wrong. So what we're going to do, since we want to make sure and include everything to the right of 152, we don't want to go from here because then we would miss anything in here, all right? So we actually want to start at 151.5. I know it seems kind of weird. Why don't we just do 152? But that's this continuity correction. We're actually going to be looking at everything to the right of 151.5. That's our correction. We're fudging the numbers just to make sure and cover our bases. So at this point, we've got everything that we need to do exactly what we did in the last few sections. If you're going to use the table, you're going to have to change that into a z-score number. Remember, the z-score would be like our x number minus the mean over the standard deviation, but I don't want to do that. Everyone either has access to a calculator or a website, so it doesn't make sense to me to have to change to a z-score and look at the z-table. All right, so instead of doing this, I'm just going to use my numbers as is. And I'm going to use the normal CDF function. We want greater than or equal 152. And it makes sense to me when I look at that picture. I want between 152 and infinity. From 151.5 actually with a correction to infinity. I'm going from 151.5 to infinity. So when you, when you do your normal CDF, the left bound, the left side is 151.5. It's going all the way to infinity. Well, we can't type in infinity in our calculator, so just type in something really big. I like a bunch of 9s. Typing in a bunch of 9s is kind of simulating infinity in our equation. And then we type in the mean, and then we type in the standard deviation. So type that in real quick. You got your calculator, do that. If you don't have a calculator, you're going to type it into that website, the normal probability distribution. Anybody have it? Type it in yet? Approximately 0.2665. That's what I got. So go back and look at the question again. Find the probability of getting 152 or more yellow peas by random chance. There we go. Okay, that is our approximation for the binomial. Second part of that question says, is that number significantly high? Well, we got 26%. We were expecting it to get 25%. That's pretty darn close. So I would say this is not significantly high. Here's this continuity correction again. It seems kind of repetitive, and it is. Add or subtract 0.5. A little bit weird why we did that, but we had to do that to account for the continuous probability of the normal distribution as opposed to the discrete of the binomial. Okay, so here's everything that could have happened in that problem. All right, when they say at least 152, that's what we just did. We wanted greater than or equal 152. But there are other things that could happen. If they want more than 152, then you take out the equal sign. And if they say at most 152, then that would be like less than or equal 152. And if they say fewer than 152, then take out the equals. If they say exactly 152, that's just an equals. There's only those 5 things that could have possibly happened. They asked us the first one, but they could have asked us any one of those 5 in this problem. Now, I want to talk about this continuity correction for these 5 different things. And I don't have a whole lot of room, but I think I can do it in this amount of space over here. Imagine our normal curve. And the number was 152, but with the correction, we're looking at 151.5 and 152.5. All right, so those 2 vertical lines with 151.5 and 152.5 happen to split my curve into 3 regions. 3 regions. Region 1, Region 2, and Region 3. And so what we want to do is kind of look at each of the 5 situations compared to those 3 regions. When we want to be greater than or equal to 152. We want to be to the right of 151.5. That means we're in regions 2 and 3. More than 152, we are only going to choose region 3 to the right of 152.5. Again, remember, we're just approximating and we're kind of fudging the numbers a little bit. All right? To the left of 152, this time we're going to be regions 1 and 2. That would be to the left of 152.5. And less than 152 or fewer than 152, we're only going to be to the left of 151.5, region 1. And then exactly equal to 152, we're going to be between 151.5 and 152.5, or just region 2. I think that's a little bit confusing, but those are the 5 different possible things that could happen. We just did the first one, but maybe we do the second one or the third one or whatever the next time. Number 2, using the same information from example 1, find the probability of exactly 152 yellow peas among the 580. Okay, so you think about what we had. What we had in that last problem, the mean was 145, and the standard deviation was 10.4283. And they gave us 152, but with our correction, we corrected to 151.5 and 152.5. Okay. So in this case, they want the probability of exactly 152. So in this case, we want the region that's in between those two numbers. That's what we're going to look at. All right, the region between 151.5 and 152.5, that's what we're looking at. And so just think about, here's the left side, here's the right side. We're using those two numbers along with the mean and the standard deviation. So we can do our normal CDF going from 151.5 to 152.5. Mean is 145, standard deviation 10.4283. Feels very similar to what we've been doing, right? All you have to do is draw that picture out and figure out what the left side and the right side is. Again, if you wanted to use the chart, you're going to have to convert those X numbers into Z-scores. I don't want to do that though. Let's just do this. You type that in, you get about 0.0305. The last part says, is this result useful for determining whether 152 yellow peas is significantly high? I don't really know. I mean, that's a tough question to just answer. I don't see it. Okay, I would say no. It doesn't look like it really tells me much of anything. I would have to do another calculation. I would have to do another calculation to tell for sure, but I would say not useful to determine if significantly high. this last slide says technology makes it less important to be able to approximate a binomial distribution. So essentially what it's saying on this last slide is we don't really even need to do anything in this whole lesson because we can actually calculate it using our calculators and our computers and stuff like that. So we go back and we look at something that we've done before with binomial probability distribution, and we see this number for x equaled 152, okay? And we compare that to our approximation, 0305 is what we got a second ago, and we see that our approximation was pretty good, but I'm not sure that we even needed to go there because our calculators can do so much now. It's interesting to know that we could. Keep in mind, back in my day, we didn't have this kind of stuff, and we would have had to have done a different kind of method. So, with your binomial CDF, remember C stands for cumulative. They go 1 minus in order to get the area on the right side. The way this formula works is a CDF is going to add from 0 up to 151. So by saying 1 minus, they're getting this side and not this side. But anyway, their answer of 0.2649 looks pretty close to our approximation of 0.2665. So again, our answers were approximations. They weren't perfect, they weren't exact, but they were pretty darn close.